Here are 5 mind-blowing facts from the discussion on the energy consumption of a hypothetical 1,000 trillion parameter foundation model compared to a country like Bangladesh, presented in a tabular format. Fact number: mind-blowing fact regarding 1,000 TAI model energy versus Bangladesh. 1. A single training run for a 1,000 T parameter AI model could consume an estimated 342 to 427.5 terawatt-hours, potentially equivalent to 3 to 3.7 times the entire annual electricity consumption of Bangladesh. If such a 1,000 TAI model were operated globally at a scale comparable to today's major search engines, its annual electricity consumption could be nearly 100 times that of Bangladesh, potentially exceeding 11,000 terawatt-hours. 3. The sheer energy estimated for training a 1,000 TAI model just once, hundreds of TWh, is enough to power tens of millions of homes for an entire year. 4. Even under optimistic scenarios for operational efficiency, the annual electricity demand for running a 1,000 TAI model could still be over 3 times Bangladesh's total yearly national electricity consumption. 5. The immense energy demands are due to the quadrillions of parameters and the need to process an equally vast dataset, requiring over 1 septillion, 10^30 computational operations for training alone. Predicting when a 1,000 trillion, 1 quadrillion parameter foundation model might come into existence is highly speculative. Given the current trends and the monumental challenges involved, we are likely looking at a time frame that spans decades, contingent on multiple fundamental breakthroughs occurring. Here's a detailed breakdown. Some models doubling every few months. The growth in training compute for the very largest models has reportedly slowed significantly since around 2022. This is due to the escalating costs, engineering difficulties, and diminishing returns when simply scaling up existing architectures without corresponding improvements in data, algorithms, and efficiency. Shift in focus. The emphasis in AI research is increasingly shifting from merely increasing parameter counts to enhancing algorithmic efficiency, improving data quality and utilization, as suggested by chinchilla scaling laws, for instance, developing more capable architectures, and optimizing training and inference processes. Beyond current paradigms, reaching 1,000 T technology, it would likely require paradigm shifts, major hurdles to overcome, influencing the timeline. 1. Algorithmic breakthroughs, the biggest uncertainty. Current transformer architectures, while powerful, face efficiency challenges, e.g., attention mechanisms, when scaled to extreme sizes. Entirely new, more parameter-efficient and computationally lighter architectures may be needed. Innovations in areas like extreme sparsity, conditional computing, beyond current mixture of experts, and fundamentally different ways for models to learn and represent knowledge are crucial. Without such breakthroughs, the computational and energy costs would be simply insurmountable, as discussed previously. 2. Hardware and infrastructure development, compute power. While AI hardware, like GPUs and TPUs, continues to improve, the sheer amount of compute needed for a 1000 T model is staggering. We would need many generations of improvement in processing power, memory capacity, and interconnect bandwidth. Energy efficiency. As highlighted in our previous discussion, the energy consumption of such a model using current or near-future technology would be astronomical. Orders of magnitude improvements in flops per watt are essential. This might necessitate novel chip technologies, e.g., optical computing, advanced neuromorphic chips, 3D stacked architectures, beyond current silicon roadmaps. Infrastructure scale. The physical data centers required would be city-sized, demanding immense investment in resources. 3. Data requirements. The data famine. Training a 1000 T model effectively would require datasets orders of magnitude larger and more diverse than what is available today. The challenge of curating or generating high-quality, unbiased data on this scale is a massive hurdle. 4. Economic viability and investment. The cost to design, train, and operate a 1000T parameter model would likely run into the hundreds of billions, if not trillions of dollars. Sustained, massive global investment would be necessary, driven by exceptionally compelling use cases or national strategic interests. 5. Energy availability. Beyond efficiency, the sheer quantity of energy needed, potentially multiple times a country's annual consumption for training and operation. Expansion of global clean energy production. Possible, highly speculative timeframes. Optimistic scenario, requiring rapid consecutive breakthroughs. If we see a series of major, unexpected breakthroughs in algorithms, hardware energy efficiency, and perhaps even new physics for computation starting very soon, one might speculate about seeing very early stage research or highly specialized 1000T models in 20 to 30 years, i.e. 2045 to 2055. This is extremely optimistic. More realistic, but still speculative scenario. Given the scale of the challenges and the typical pace of fundamental scientific and engineering revolutions, it's more probable that if such models are achievable, they are many decades away, possibly 30 to 50 plus years, i.e., post-2055 to the latter half of the century. Pessimistic scenario / paradigm shift required. It's also possible that current AI paradigms will hit fundamental limits long before 1000T parameters are reached. In this case, such a model might only become feasible after a complete shift in our approach to artificial intelligence, making any timeline based on current trends irrelevant. Intermediate milestones as indicators. Progress towards developing robust and widely usable models in the 10T and then 100T parameter range will be key indicators. How quickly and efficiently these intermediate scales are reached, and what breakthroughs enable them, will offer better clues for the feasibility and timeline of a 1000T model. As of May 2025, even 100T models are largely considered research frontiers with no firm deployment timelines. Conclusion. While the AI field is dynamic, the leap to a 1000T parameter model is so substantial that it's beyond any clear predictive horizon based on current trends alone. It's less a question of when, based on simple extrapolation, and more a question of if and how the monumental scientific, engineering, economic, and energy challenges can be overcome through sustained innovation and multiple breakthroughs. Expect this to be a very long-term endeavor, likely spanning several decades at best. Predicting the exact year a 1,000 trillion, 1 quadrillion parameter foundation model will come into existence. A 1000T parameter AI model is likely several decades away, as its creation hinges on fundamental breakthroughs to overcome massive data, energy, cost, and algorithmic hurdles, rather than being a simple extrapolation of current trends.